Welcome to the EVPN Overview module. By the end of this module, you should be able to describe the basics of EVPN routing and bridging.
A virtual extensible LAN or VXLAN environment is a Layer 2 VPN. Terminology in an Ethernet VPN, virtual extensible LAN, or EVPN-VXLAN environment resembles that of a traditional VPN environment, including the concept of provider edge or PE devices or a VPN edge device that performs encapsulation and decapsulation, such as VXLAN gateway or virtual tunnel endpoint or VTEP.
These are often referred to as leaf nodes.
Customer edge or CE devices are a device that is associated with the customer site. In a data center, a site is often referred to as a host, physical or virtual, that is connected to a leaf node. Sites are a set of hosts or virtual hosts connected to a VTEP gateway. It is common to have multiple hosts or virtual hosts that participate in the same virtual network connected to the same VTEP or leaf node. Regardless of the underlay routing protocol, IBGP or EBGP is used for the EVPN control plane signaling.
EVPN instance or EVI is a virtual switch within a VTEP. It is a MAC VRF routing instance that is unique to a broadcast domain. Because multiple broadcast domains may be connected to a single VTEP, the VTEP maintains a separate MAC VRF for each instance to maintain traffic isolation between broadcast domains. A bridge domain is equivalent to a VLAN. It is a Layer 2 broadcast domain within a VXLAN environment. There can be many bridge domains for a single EVI. The route distinguisher is a value that is combined with routes that are advertised in a VPN environment. The route distinguisher ensures that routes in a multi-tenant domain are unique when advertised. A data center is a multi-tenant service provider environment where tenants are hosts that belong to independent broadcast domains, and the data center is the service provider that interconnects those hosts. When routes are advertised within the data center or service provider environment, they may be stored in local RIB-IN databases on each PE device or leaf node. To avoid any overlap of the site addresses between different broadcast domains, a route distinguisher that is unique to each Ethernet segment is prepended to each route before it is advertised to remote PEs. In the example, two clients or broadcast domains are using the same IP prefix of 10.1.1.0/24. The route distinguisher enables the service provider to distinguish between the 10.1.1.0/24 network of each customer by making each network address unique while it transits the provider domain. The route distinguisher can be formatted in two ways. Type 0 format uses a 2-byte administration field that codes the provider's autonomous system or AS number, followed by a 4-byte assigned number field. The provider administers the assigned number field and should be unique across the AS. Type 1 format uses a 4-byte administration field that is normally coded with the router ID or RID of the advertising PE router, followed by a 2-byte assigned number field that carries a unique value for each virtual routing and forwarding or VRF table supported by the PE router. The example shows both the Type 0 and Type 1 route distinguisher formats. The first example shows the 2-byte administration field with the 4-byte assigned number field, Type 0. The RFC 7432 BGP-MPLS-based Ethernet VPN recommends using the Type 1 route distinguisher for EVPN signaling. Each EVPN route advertised by a PE router contains one or more route target communities. These communities are added using VRF export policy or explicit configuration. When a PE router receives route advertisements from remote PE routers, it determines whether the associated route target matches one of its local VRF tables. Matching route targets cause the PE router to install the route into the VRF table whose configuration matches the route target. Because the application of policy determines a VPN's connectivity, you must take extra care when writing and applying VPN policy to ensure that the tenant's connectivity requirements are faithfully met. VRF export policy for EVPN is applied using the VRF target statement. In the example, the statement VRF target:1:1 is applied to Leaf 2's orange EVI. The statement causes all locally learned MACs in the MAC table to be copied into the VRF table as EVPN Type 2 routes. Each of the Type 2 routes associated with locally learned MACs is tagged with the community target:1:1. These tagged routes are then advertised to all remote PEs. The VRF target statement always sets the target community using hidden VRF import and export policies on Type 1 routes. By default, the VRF target statement also sets the target community of Type 2 and Type 3 routes as well. VRF import policy can be applied using the VRF target statement, or it can be enabled by manually writing a policy and then applying it with the VRF import statement. The VRF target statement is used to enable an export policy that advertises EVPN routes tagged with the target community. The statement also enables the associated import policy, which accepts routes that are tagged with that target community. At a minimum, configure the VRF target statement to enable the export policy. To override the import policy instantiated by that statement, you can apply the VRF import statement. In the example, the VRF target:1:1 is applied to Leaf 2's EVI. When Leaf 2 receives the MAC advertisement from Leaf 1, it runs the route through the configured import policy, which accepts routes tagged with target:1:1. Once accepted, the route is copied into the Leaf 2's global RIB-IN table and then copied into the appropriate VRF table, the one configured with the VRF target:1:1 statement. Finally, the route is converted into a MAC entry and stored in Leaf 2's MAC table for the green EVI. The outgoing interface associated with the MAC is the VXLAN tunnel that ends on Leaf 1. When EVPN signaling is used with VXLAN encapsulation, Juniper Networks devices only support ingress replication of broadcast, unknown unicast, and multicast or BUM traffic. When BUM traffic arrives on a VTEP, the VTEP unicast copies of the BUM packets to each of the individual VTEPs that belong to the same EVI. This is the default behavior and setting on a device running the Juno's operating system. Ethernet VPN or EVPN routes are classified according to route types. Each route type performs a specific task in an EVPN environment. There are 11 EVPN route types. However, 8 of them are shown here. Type 1, Auto Discovery or AD route. Type 2, MAC or IP route. Type 3, Multicast route. Type 4, Ethernet segment route. And Type 5, IP prefix route. The following route types are described in the EVPN Multicast Extensions module. Type 6, Selective Multicast Ethernet route. Type 7, IGMP join sync, and Type 8, IGMP leave sync. A BGP route advertisement comprises a destination prefix. The prefix that is advertised includes a set or properties associated with that prefix. These properties are used for a variety of tasks. One property is called the protocol next hop. The protocol next hop property lists the remote gateway to use for reaching the advertised prefix. The remote gateway, or the protocol next hop, is not always set to the device that advertises the route, since an advertising router may relay the route from another peer. If a route prefix is received by a BGP router, the BGP router must validate whether the remote gateway to the prefix is reachable in the local routing table, also known as Routing Information Base or RIB. After all, a device can't forward an IP packet towards a remote gateway if the device does not have a route towards that gateway. The process of validating the protocol next hop of a received route is called a recursive lookup. A recursive lookup describes searching within a local routing table to find a physical next hop that points toward a received remote next hop or gateway address. With an IP prefix, the local router examines the entries in the local inet.0 routing table to determine the next physical hop toward the advertised protocol next hop. The physical next hop to the remote gateway is then associated with the advertised prefix and installed in the local routing table as the physical next hop for the advertised prefix. With an MPLS VPN route, an MPLS destination must be reachable through an MPLS tunnel. MPLS tunnels are installed in the inet.3 routing table, and therefore all MPLS VPN advertised routes must have a route to the protocol next hop present in the inet.3 routing table. With an EVPN advertised destination, the EVPN destination must be reachable through a VXLAN tunnel before it can be placed in the local BGP.EVPN.0 routing table. The VXLAN tunnel routes are installed in the :VXLAN.inet.0 routing table. Therefore, when an EVPN route is received by a router through multi-protocol BGP or MP-BGP, the route to the protocol next hop of that prefix, which is the loopback address of the remote VTEP device, must exist in the :VXLAN.inet.0 route table. When a local subnet is configured as a virtual network identifier or VNI, the local interface is added to the :VXLAN.inet.0 table. When a remote VTEP is discovered, a route to the remote VTEP loopback is placed in the :VXLAN.inet.0 table as an automatically generated static route. The VTEP logical tunnel interfaces are created when a remote VTEP advertises connectivity to one of the VNIs that is configured locally. If a remote BGP peer advertises an EVPN route for a VNI that does not correspond to a locally configured VNI, then the local VTEP will not have a VTEP tunnel to the remote gateway, and therefore will not have a route to the protocol next hop. This causes the local VTEP to drop the advertised EVPN prefix, because the prefix is for a VNI that is not associated with any locally configured VNIs. This saves resources by not storing routes to remote VNIs that are not configured locally in the BGP.EVPN.0 routing table. When a host is multi-home to multiple leaf nodes, the link aggregation group or LAG represents a single logical connection to the VXLAN domain. A unique Ethernet segment identifier or ESI is assigned for the EVPN control plane to properly manage the multiple links in the LAG. By default, a single-homed link is assigned the ESI value of 0. A single-homed site does not require loop prevention or load sharing across multiple links. With a multi-home site, a unique 10-octet ESI must be assigned to the link bundle. The same ESI value enabled on the multiple leaf switch interfaces connected to the same server to create an EVPN lag. This EVPN lag supports active-active multi-homing toward the connected server. This ESI value can be configured to be derived automatically from the Link Aggregation Control Protocol or LACP configuration, or assigned manually by the administrator. When configuring the system for automatic ESI values, use the ESI Auto-Derive option. The system uses the LACP system ID configured by the administrator to derive the aggregate Ethernet ESI and the VLAN ID to derive the logical unit ESI. If you are manually assigning ESI values, it is recommended using an ESI value that uses the same values for the first 8 bytes with changes only in the 9th and 10th bytes on a per EVPN lag basis as shown here. Using a structured ESI assignment method simplifies network administration. If your environment has a standard numbering for site identifier, floor, or server, you can incorporate this numbering into the first 8 bytes and leave the last 2 bytes for sequential numbers. In the example, the lag that connects CE1 to leaf 1 and leaf 2 is assigned a value as shown here. This enables the EVPN control plane to identify that the device connected to leaf 1 and leaf 2 over link A and link B are the same site. Because the EVPN control plane advertises the ESI associated with the lag group to all VTEPs, remote VTEPs install multiple next hops associated with MAC addresses assigned to CE1 and 2 VXLAN tunnels are available for forwarding. In addition, leaf 1 and leaf 2 can manage the lag bundle without implementing multi-chassis lag or MC lag, and traffic loops and traffic replication between the two lag interfaces can be prevented.